the morning until lunch. You get an hour and a half now. At 10:30 we break for coffee for half an hour, and then we continue.
Perfect.
Go ahead, Pratika.
Thank you very much, Ricky. Okay, so good morning, everyone. So my name is Pratika, and I'm a professor at the Canadian Institute for Theoretical Astrophysics. So I moved there a month ago. So I think a lot of you knew me from my time in Groningen, but yes, so now I'm in Canada. And what I will, before I start, I think I should thank Rosa and Roland for organizing this amazing meeting and for giving us this opportunity to come here and really just to learn from each other. I have a lot of stuff, but we don't actually have to go through all of it. I think it's much more important that concepts get across. So if there's anything which is unclear, please just feel free to stop me, and then we can have a chat. OK, so what I would like to do is just give you a global introduction to the physics of reionization, which includes what are the key problems that we are facing in the field of reionization, what exactly is this process, what are the key drivers, what are the open questions, and what exactly have we learned from all of this new data that has come from the James Webb. So let me very quickly start with these are some of the key questions which I'm going to try and address. I would really like for this to be interactive, so please feel free to shout out answers. So the questions that are the key open questions in the field of reionization are what were the key sources of reionization? So I'm not going to give you answers, but so yeah, what were the key sources in the early universe which were driving this process? A question that Laura Penterici is going to discuss in much more detail is how exactly did the photons that these early sources were producing, how did they actually get out of the galactic environment and into the intergalactic medium? This is really an unsolved problem in the field of reionization. How exactly did reionization progress through time? For a huge amount of time, people were just assuming reionization was a step function, so it was really an instantaneous process. And I'm just going to show you that as time has gone by, this view has evolved into one where reionization was a really patchy, a very gradual process, which seems to just start very early and keep lingering on. And this is one of the key problems we are facing with in terms of James Webb data. And did reionization have any sort of feedback effect on the key sources that were driving the process? So these are the key open questions that I'm going to address. But before I jump into this, I thought what would be really important is to try and put reionization into a cosmological context. So I think you've all heard this from Andrea's presentation, but let me restart and start with the start of the universe, which is, we think, in something called the Big Bang, roughly 13.8 billion years ago. I think you all know that after the Big Bang, the universe was basically just underwent a period of inflation where it expanded by more than 60 orders of magnitude in a really, really short amount of time. So this was 10 to the minus 36 to 10 to the minus 32 seconds. Now, after inflation, the universe was basically just expanding. As it was expanding, it was cooling. Now, at a redshift of about 1100, which is roughly 400,000 years after the Big Bang, for the first time, the universe was cool enough that electrons and protons could combine to form neutral hydrogen. At this point, matter and radiation get decoupled from each other, giving rise to the cosmic microwave background. So please remember, this forms roughly 400,000 years after the Big Bang. So this is really the first snapshot, or the earliest snapshot that we have of the universe. Now, the period after this recombination of electrons and protons and decoupling between matter and radiation is followed by what is known as the dark ages in the history of our universe. And this period lasts from a redshift of about 1100 to a redshift of about 40 or 30 whenever you think the first stars actually start forming. So this period, which lasts for the first few 100 million years of the universe, is called the cosmic dark ages because at this point, what is happening is that dark matter is trying to collapse to form halos, but baryons are not yet falling inside these halos, cooling and forming stars. So really, the universe is very dark, and the only photons you have are the photons of the CMB, which are now free streaming throughout the universe because they see no optical depth. Now we get into the era of cosmic dawn when the first sources turn on. So it is anybody's guess as to when the first stars form. So Andrea gave us a really nice introduction on the formation of the first stars. So can I ask you guys to give me some sort of an answer on when you think the first stars were actually forming? What was the redshift of the formation? I'm just really curious because, you know, what do you think? Shout out numbers. 30. Okay. Is everybody converging on 30? I don't know. Or 42, right? No. Okay, so this is actually one of the key open questions. We don't actually know when the first stars were forming. So there were calculations which were done which came up with an answer of 42, so it's really not a joke. People were proposing this was one of the redshifts at which some of the first stars could start forming. But this is really an open question. We don't know the exact precise redshift. It could have been more gradual, so looking for the first stars in the universe is really an open question, as you've heard from yesterday's lecture. So this is the era of cosmic dawn when the first sources are turning on, and these are metal-free stars which are forming out of primordial gas, which is hydrogen, helium, trace amounts of lithium. Now comes the topic of today's lecture, which is the epoch of reionization. And we will get into the details of this, but what I would like for you guys to note is all of these little dots that you see here are sources. They could be whatever. So these are just sources which are producing hydrogen ionizing photons, which are more energetic than 13.6 electron volts. Remember that at this point, these galaxies are all embedded in this gas, which is hydrogen, helium, trace amounts of lithium. When you produce hydrogen ionizing photons, you can ionize a certain patch of the universe around yourself. And we're going to see how much of the universe you can actually ionize. And these ionized regions are shown by these grayish patches. So even from this really simple illustration, you can see that reionization is a very, very patchy process, which starts in the regions where you have the formation of the sources of ionizing photons. These regions are then overlapping with each other. So what is basically happening is if you have galaxies forming nearby or any source which is producing ionizing photons, if they are sitting close by to each other, they produce these ionization regions which start overlapping. As more and more stars keep forming throughout cosmic time, these regions start growing, overlapping. You have more and more regions until at some point these ionized regions cover all of the available volume of the universe. And at this point, you say the epoch of reionization is complete. So the initial stages of this process remain really mysterious because we don't exactly know what were the sources that were forming, how many did we have, and when were they forming. But as I'm going to show you, the end stages, which are somewhere about a redshift of 5 to 6, are much more clear. So we do have some sort of a constraint on when this process was ending. I would like to note that the universe is basically 75% hydrogen, 25% helium in terms of baryons. For the purpose of this lecture, I'm going to completely ignore helium. The first sources are actually energetic enough. So black holes or metal-free stars are energetic enough that they can produce helium ionizing photons. But we're going to completely ignore this for the purposes of this talk and only focus on hydrogen reionization. If you're interested in helium reionization, please come have a chat with me later. Okay, so once the epoch of reionization is complete, the universe is now basically full of ionized hydrogen. And you might say, well, why should I care about something which finished at a redshift of 5-ish? The reason is that this was the last major phase change of all of the hydrogen in the universe. Once reionization was complete, at a redshift of 5 or 6, somewhere within the first billion years. For the next 12.5 billion years, the neutral hydrogen has remained ionized. So since the epoch of reionization, after this last phase change of hydrogen, all of the hydrogen in the universe is completely ionized. So for all those of you who work on Milky Way studies, you might have heard that reionization can have an effect on quenching low-mass galaxies, even in our local universe. So I'm going to show you how reionization has actually impacted all of the structures that were forming not just during the epoch of reionization, but all the way down to the present universe. Okay, so let me now very quickly show you a movie on how we think reionization happens. In the lower left corner, you are going to see the redshift. So this is one simulation which shows you how reionization takes place. All of the pink dots that you see, Okay, all of the pink dots that you see are sources of ionizing photons. The black color shows you neutral hydrogen, and the whitish color shows you ionized hydrogen. So this movie is going to keep running in a loop. So we start at early times. As time goes by, more and more sources are forming. These are ionizing the regions around themselves, which are continuously growing and overlapping, until a redshift of roughly about 5-ish or so, when these ionized regions cover all of the available volume of the universe, and you say the process of reionization is complete. What I really want you guys to remember from this is that reionization is a very, very inhomogeneous process. It starts in the regions where you have the sources of ionizing photons, and then it percolates all the way into the intergalactic medium. How it percolates into the intergalactic medium is a really complex problem that I'm going to detail a bit more in the second lecture. Okay, so let me now quickly show you the key stages of the reionization process. So in the beginning, you have individual sources which are ionizing regions around themselves. This is what we call the pre-overlap phase of reionization. So you really have individual objects which are just building an ionized region around themselves. As time goes by, you will start to form sources in overdensities, and I think you all know overdensities are clustered. So wherever you have one overdensity, wherever you have some sort of a source forming, it's more probable something else is going to form in a given nearby overdensity. So you have source formation in these nearby overdensities, and the ionized regions from these sources start overlapping, which is called the overlap phase of reionization. So this is the phase when you're really trying to percolate these ionized regions into the large-scale intergalactic medium. Now at some point, as we were discussing, you will have enough sources which will produce enough ionizing photons that you can cover all of the available volume of the universe with these ionized regions. And now note, this basically becomes like a background. These are no longer individual ionized regions, but the overlap is so vast that it covers basically all of the available volume. And so now this just becomes like a continuous background of ionized regions. And this is what we call the end stages of reionization. So we're really looking for a situation where instead of individual ionized regions, you're really sitting in some sort of a continuous background. And this is called the post-overlap phase of reionization. And so the idea is that if you would look in more or less any direction, you should see the same reionization background. This is actually one of the key indicators of the fact that reionization is complete. When you basically start to see the same optical depth, irrespective of which direction you are looking at, which tells you that you are sitting in a continuous homogeneous bath. So now you could say, well, okay, this is all very good, but do we actually have any evidence that reionization took place? So can I ask you guys, what evidences do we have that reionization ever took place for this many people here who are experts? Very good, quasar spectra, okay. What else? Okay, very good. This is a very good answer. Yes, okay. Sorry? What do you mean? Do you mean the break blue word of Lyman alpha? Okay, good. More or less, you guys have covered all of the things we are using to probe reionization. So, okay, let me go step by step. So the first method that we use is looking for absorption in the intergalactic medium. So this is something that Claudia actually works on. You're going to give a presentation on Friday, I think. Yep. Okay, so the idea is as follows. Here is a very powerful background source So in this case, this is a very, very luminous quasar. So we're basically just going to call it a quasar. It's basically an accreting black hole, but which is extremely luminous. Now here is the line of sight from this background quasar to us. And along this line of sight, you have a huge number of sources, which you can maybe see with the whitish dots. And the regions that they are ionizing around themselves are these yellowish patches. So I'm going to explain this a little bit more in detail. But basically, this quasar is going to produce a spectrum, which includes the Lyman alpha line. So here is the Lyman alpha line that the quasar is producing. We're going to see this in a second on the next slide, but the optical depth of Lyman alpha photons against neutral hydrogen is extremely high. So now, as this Lyman alpha line moves away from the quasar towards the observer, wavelengths that are shortward or blueward of Lyman alpha will get redshifted into absorption with neutral hydrogen along the line of sight. So as the quasar spectra is propagating, what will happen is wherever you have these regions which are ionized, you will have what we call transmission spikes. Wherever you have regions that are completely neutral, so the blue color here just shows you neutral hydrogen, you will have these patches which are called dark gaps where no flux is transmitted. So basically, you can use these transmission spikes as indicators of ionized regions between the line of sight, between the quasar and the observer. This is a method that was actually proposed by Gunn-Peterson. So they said, if the universe were to be completely neutral, all of the wavelengths blueward of Lyman alpha would basically be completely absorbed. You would see nothing. So this is called the Gunn-Peterson trough, which you have all heard about. So if you try to put this into equations, basically what we are trying to do is calculate the optical depth to Lyman alpha photons. These are photons at 1216 angstroms in the rest frame of the source. So we're going to calculate the optical depth of Lyman alpha photons against neutral hydrogen. And so you have some sort of a cross-section, which depends, of course, on the frequency. So here, the frequency is written in the observer's frame. You can also do it in the source frame. So you have some sort of a cross-section. And what you are doing is you are trying to integrate at any given point between the source and the observer what is the density of neutral hydrogen. And this is just the integral over the total line of sight. If you try to look at the term which is the cross-section, this basically depends on the electron charge, electron mass, and it also depends on the line profile. So what is the actual absorption profile of neutral hydrogen towards wavelengths which are close to the Lyman alpha? For the purposes of this presentation, we're basically going to assume that this absorption or this scattering basically peaks at the Lyman alpha luminosity. So you can just treat this term, which is the line profile, you can just treat it as a monochromatic term, which is basically just the Lyman alpha frequency. So you can then you can solve dl over dz in terms of the Hubble parameter as a function of redshift. If you guys are interested, please just go solve this yourselves. It's very easy. The end result is that the total optical depth that you have can be expressed in terms of the matter density and baryon density parameters, which you know from cosmology. And it depends on the redshift, because this is the term that is going to determine the total line of sight between the source and the observer. What is really crucial is this term, chi h1, which you will keep seeing in reionization. And this chi h1 basically tells you the fraction of hydrogen which is neutral. So people will generally write this as number density of neutral hydrogen over the number density of hydrogen. This is your chi h1. So this will keep appearing throughout this lecture. And what I want you to note is that the optical depth has this value, which is about 10 to the 5, ignore all of these terms, times chi h1. So if 1 part in 10 to the 5 of your hydrogen atoms is neutral, you basically end up with an optical depth of 1. So this Lyman alpha line is a very, very sensitive probe of the total neutral hydrogen content between the source and the observer. And this is what Gunn and Peterson were proposing. So basically their idea was if you have even a tiny amount of neutral hydrogen between the source and the observer, the optical depth is going to be 1. And so if this is your source spectrum, and I'm treating this as the Lyman alpha line, everything that is blueward of the Lyman alpha line will basically get attenuated. So all of this part of the spectrum is basically going to disappear because of absorption by neutral hydrogen between the source and the observer. So what you're going to see is a steep cut off in terms of your spectrum, and this will happen at the Lyman alpha wavelength, which is 1216 angstrom in the rest frame of the galaxy. This dip is what is called the Gunn-Peterson trough, because it's a sudden trough, which is blueward of the Lyman alpha. So this is the indication, the first indication we were looking for when we were trying to map out when exactly did reionization happen. So one of the first observations came from the SDSS, and this is now almost 20 years ago. So this is work from Fan et al. In 2006, where they collected spectra of 19 quasars between redshifts of 5.7 and 6.4. So redshift moves upwards, so these go from 5.7, and as you go up, this is a redshift of 6.4, and they are arranged in terms of increasing redshift. So what I want for you to notice is that, sorry guys, can everybody see the bottommost spectrum? Okay. So here is your Lyman alpha line, and you know there has to be a steep break blueward of the Lyman alpha, so you can kind of figure out this is your Lyman alpha line somewhere here. But if you're at a redshift of 5.7, you can see a little bit of transmission blueward of the Lyman alpha. So this means there must have been some ionized regions between the source and the observer. As you go to increasing redshifts, the Lyman alpha line is shifting to higher and higher wavelengths, because this is just 1216 times 1 plus z. So you can see that the break is shifting to increasing wavelengths as you go to higher redshifts. And what you generally find, not for every source, but statistically, is that these dark gaps, which signify complete absorption blueward of the Lyman alpha, become more and more prevalent as you go to higher and higher redshifts. So at the first instance, this basically just tells you as you come to lower and lower redshifts, you have more and more ionized patches in the universe. This was one of the first indications that reionization is not a step function. It's a very inhomogeneous process, and people have tried to use a combination of these transmission spikes and these dark gaps to actually look at what were the masses and the physical extents of these of the sources of neutral hydrogen sitting between the source and the observer. So this really was one of the first statistical observations of the Gunn-Peterson trough. So this is really a seminal paper. So for everybody who is interested in reionization, you're going to come upon this paper at one point or another. Okay, so you can also try to look at this statistically and plot the Gunn-Peterson optical depth as a function of the redshift of the source. All of these black points that you see are, so this is, these here are that I have just shown you from the SDSS. So the data at redshifts between 5.7 and 6.4, which was the highest redshift estimates that we had for the Gunn-Peterson trough. So now a really interesting trend emerged. If you look at low redshift data, the Gunn-Peterson optical depth basically scales as 1 plus z to the power 4-ish. However, if you look at this high redshift data, you can see it has a lot of variation in terms of the optical depth that you're inferring. So for some sources, you have really low-ish optical depths of a factor 2. For others, the optical depth is as high as a factor 6. So for these kind of sources, you're basically not seeing any transmission. It's a complete absorption, which means that these are embedded in a region that is quite neutral, or the lines of sight are basically quite neutral. So if you try and infer how the optical depth evolves as a function of redshift, at redshifts above 5-ish, suddenly the slope steepens to 1 plus z to the power 11-ish or so. So now this was a surprise, because why should the optical depth evolve at a redshift between below 5 and above 5, going from a power of about 4.3 to a power of 11? So this is again work from Fan. There were a number of follow-up papers which have tried to use this data to shed light on different aspects of ionization. I'm not going to go into it. If you're interested, please come ask me more. But something that Fan et al. Did was a really simple calculation where they said, if all of this optical depth is purely driven by the increasing density of the universe with increasing redshift, so because I think you guys all know that the density of the universe scales as 1 plus z cubed, rho naught, which is the density at 0. So as you go to higher and higher redshifts, the universe is becoming denser. Could all of this purely rise from this increasing density? That is this dashed line that you see here. And what you see is that these values that you are inferring for the optical depths are much, much higher than what is allowed by a pure density evolution. So the result that they, or the conclusion that they drew from this was that in addition to an evolution of density in hydrogen, you also need a steep rise in the number density of neutral hydrogen atoms. So again, it's kind of leading you back to the same place, that as you go to higher and higher redshifts, along different lines of sight, you're beginning to see a huge amount of fluctuation in the total amount of neutral hydrogen that is present between the source and the observer. Now, can I pose a question to you guys? As I've shown you, all of this is based on 20 quasars, right? So this is based on 20 lines of sight. And of course, you can break up this spectrum into different chunks to look at different bits of transmission or these dark gaps. But you're really literally probing the IGM along 20 lines of sight. So would you say this is really representative of what is happening in the entire universe? I see like people shaking their heads. People are really depressed. Okay, good. So yeah, so this is one of the key caveats, that yes, we're limited to 20 lines of sight. And although you can break up the spectrum into chunks, you are really probing specific lines of sight. And remember that quasars are extremely, extremely luminous black holes, so they live in very overdense environments, which are not representative of structure formation in the entire universe. And so this is one of the key caveats that you should keep in mind when you try and look at this. But nonetheless, this is the best data set that we had up to a few years ago, and I'm just going to show you what's changed. So in 2022, there was a group from Heidelberg that carried out a project which they call XQR30. And they looked at now 67 quasar sightlines at redshifts greater than 5.5. And now they're trying to basically update the constraints that you have on the Gunn-Peterson optical depth as a function of redshift. So now, again, they are breaking up the entire the spectrum that you get into different pieces to see, as a function of redshift, how is the transmission evolving as for these different quasar sightlines. So now, again, if you are at redshifts below 5.3-ish or so, so if you just focus on this side of the plot, all of these different points that you see are breaking up individual spectra into chunks. And the red points are the averages as a function of redshift. So this is over a delta Z of 0.1. So what I want you to note is that when you are at redshift below 5.3-ish, the scatter is not super high, so there are still sight lines which show a little bit of variation. But as you go to higher and higher redshifts, you find an increase in the scatter of transmission along these different lines of sight. So breaking up the lines of sight into different pieces, you start to see a huge fluctuation in the optical depth. Again, the same thing we were seeing in the previous data set from Fan et al., that the optical depth varies by a factor of 2 to even 4 between these different sight lines. If you look at the average or median behavior, again, you find that the optical depth is continuously rising as a function of redshift. So even with more updated quasar spectra, so now there's 67, it's not 20, so it's a factor of roughly 3 increase in the quasars that you do have. Again, it's showing you the same thing, that the optical depth is really increasing as you go to high redshifts. But crucially, along different lines of sight, you are beginning to see an increasing variation in the transmission. So this means along some lines of sight, you're encountering almost no neutral hydrogen. Along other lines of sight, you're encountering huge amounts of neutral hydrogen. So this basically tells you that the process of reionization was not homogeneous or not homogeneously complete, even down to a redshift of about 5.3. So a lot of different people are now beginning to use these to converge on the fact that it seems reionization should have ended. So as you remember, we said reionization, when reionization ends, the reionization background becomes extremely homogeneous. This is the sign we are looking for to define the end stages of reionization. So if homogeneity is your requirement, it seems like reionization should end somewhere around a redshift of 5.2-ish. Okay, so now let me take you to a more cosmological probe of the epoch of reionization, and this came from the CMB. So this was actually one of the first indicators that we had for the fact that there were free electrons in the universe in large quantities. So the idea here is as follows. You have your CMB, which formed at a redshift of about 1100. As it is traveling to the observer who is sitting over here, it's going to, in the beginning, encounter a lot of neutral hydrogen atoms when reionization has not yet started. These do nothing to scatter CMB. But the moment reionization starts, you have a collection of electrons and protons. Electrons will start scattering CMB photons. And this is basically an elastic Thomson scattering. So it's just going to scatter CMB photons along different lines of sight. So what this does is basically it smears out the CMB temperature fluctuations on very, very small scales. Because remember, this is a small scale process, so you have neutral hydrogen in the beginning just everywhere. And ionized hydrogen will be limited to the regions where you have some sort of a source which can ionize this hydrogen. Once reionization is complete, you are in a situation where the entire volume of the universe is full of electrons and protons. And so the optical depth increases a lot because now all of these CMB photons will keep scattering against these electrons and protons before they reach the Earth. What you're measuring from the CMB is this total optical depth from a redshift of 1100 to a redshift of 0. This is why this is called the integrated electron scattering optical depth. And people are generally going to denote it as tau electron scattering. But remember, this is not at any specific point in time. This is really the integrated electron scattering optical depth. So if you want to calculate this optical depth, this is between 0 and the redshift in principle of the formation of the CMB. So in principle, this should be a redshift of 1100. Thomson scattering cross section. How many electrons you have as a function of redshift? All the way, integrating all the way from a redshift of 1100 down to the present day. Now, what CMB experiments initially started doing was they assumed a step function for reionization. So this was the simplest thing you can do. This is high redshifts, this is low redshift. You say in the beginning, the universe was completely neutral. instantaneously got completely reionized. So the number density of electrons basically went from 0 to 1. And this is what they call the redshift of reionization. So this is how CMB experiments started. Now you can, as we have just discussed, reionization is not a step function. It's not an instantaneous process. So you can assume different forms for the progress of reionization. So for example, people are beginning to use Stanage functions. You can, it's really your choice what you do with the reionization history. But in the most simple scenario, let me just assume it's really a step function. So in principle, the electron scattering depth is between a redshift of 0 and the redshift of reionization, because before this, you had no free electrons whatsoever. Now, when you measure the optical depth from the CMB, it has a value from the latest Planck constraints together with a lot of different experiments from the South Pole. You get an electron scattering optical depth, which has a really, really small value, 0.054. Roughly means 1 in 20 CMB photons was undergoing scattering because of free electrons. So you can substitute this value here. You know the number density of electrons at the present day. You can put this as a function of redshift, just as number density of electrons today, 1 plus z cubed. If you integrate this between a redshift of 0 and the reionization redshift, you basically infer a reionization redshift of about 7.6. So if the universe reionized instantaneously, you would infer this happened at 7.6. So it's not such a bad estimate compared to the redshift of 5, which we are inferring from quasar probes. And this has actually come down a lot because in the initial days when I was doing my PhD very long ago, the optical depth was actually very high. And so we were inferring reionization redshifts which were as high as 10 or even 14. And so the question was, how do you reionize the universe? Because at that time, the only galaxies we knew were up to a redshift of 5. We had no way of seeing beyond. And so it was a really hard time. Like, how do you produce so many photons to reionize the universe so early on? So in some sense, things have been converging towards a much lower redshift of 7 or somewhere between 5 and 7. If you use this really, really simple model, if you use a more complicated reionization history, it will bring you closer to what quasar constraints are giving you. So this is all beginning to look quite consistent. And now let me take you to the third probe, which we were talking about, which is the galaxies which can actually emit in terms of Lyman alpha. And so these are called Lyman alpha emitters. So let me kind of very quickly talk you through the physics, which is determining the intensity of a Lyman alpha line. So imagine that you have some sort of a molecular cloud. You have stars which are forming inside this molecular cloud. These will produce hydrogen ionizing photons, and they will start to ionize this nebula around themselves. This nebula is generally extremely dense, so these are star-forming regions. So these electrons and protons will recombine on very short timescales, typically a few million years. Giving rise, and this recombination will actually give rise to a Lyman alpha line, which is why this is a nebular recombination line. So it's because of recombination within a nebula, which is ionized by whatever source. So if you want to look at the intrinsic luminosity, I'm going to assume that all of the photons, okay, let me take one step back. So let me ask you guys this thing. So imagine I have a source which is producing a lot of ionizing photons. Are all of those photons going to be involved in ionizing the gas around the source? Who all are saying no? Do we have consensus? Okay, very good. So I see hands up. People are a bit hesitant. It's okay. Like, we're going to show you this is like a really ill-defined parameter. Anyway, okay, so let's assume some fraction, which we are going to keep calling F escape of ionizing photons, leave the cloud without ionizing anything. So the only photons you have access to are those which are bound within the cloud, so 1 minus F escape. I multiply this by the total number of ionizing photons, So this is the total number of ionizations I will have. They are going to recombine to produce a Lyman alpha line. So this expression gives you the intrinsic Lyman alpha luminosity that is produced by any source, which is able to ionize the nebula around itself. Now, you can produce Lyman alpha, but this is just the beginning of the story. So here, let me show you the whitish part, which represents the interstellar medium of a galaxy. I think you all know that the ISM is full of neutral hydrogen, and it's also full of dust. So here, neutral hydrogen is shown by these clouds. All of these little dots that you see represent dust. So dust and gas are intermixed within the ISM. The ISM is a really, really complicated environment where you have a lot of turbulence. So imagine you have these ionizing photons, which ionize the nebula, produce a Lyman alpha line. So let's assume that the Lyman alpha line is these blue arrows that you see. So it's going to go off in basically all directions. Lyman alpha photons that hit a cloud of neutral hydrogen and dust are basically just going to get scattered out of the line of sight. They can be absorbed by dust, but for neutral hydrogen, it's just a scattering process, so they get scattered into random directions. So these Lyman alpha photons are basically going to be lost to you. The only Lyman alpha photons you will see are those that can somehow find empty channels of low density and that can make it out of the galactic environment. So galaxies for which some amount of Lyman alpha can actually make it out of the galaxy to make it visible in terms of a Lyman alpha emission line are called Lyman alpha emitters. So now I think what I would like to convey to you guys is that the Lyman alpha photons which escape out of the... Okay, so this is what happens with Lyman alpha, right? I mean, the optical depth is like 100%. No, I think this is actually my computer. Okay, sorry, wait. Okay, very good. Okay, fantastic, Lyman alpha. Okay, so now imagine these Lyman alpha photons, actually a fraction of these Lyman alpha photons that you produce come out of the galaxy. At high redshifts, what are these Lyman alpha photons going to see? Very good, fantastic, neutral hydrogen. So imagine I'm a Lyman alpha photon, I come out of the galaxy, immediately what I see is neutral hydrogen. Again, I will get scattered out of the line of sight. So I'm not going to reach an observer who is sitting over there. But we have been discussing that depending on how many ionizing photons galaxies produce, they can actually ionize a region around themselves. Imagine that this region is large enough that the Lyman alpha photon finds a path which is low in terms of neutral hydrogen. It's continuously getting redshifted. If this region is big enough that I am redshifted out of resonance with neutral hydrogen by the time I reach the edge of this region, then as a Lyman alpha photon, I can reach the observer. So Lyman alpha physics has actually been extremely complicated because not only are you attenuated by dust and scattered by gas within the ISM, but you are also scattered by neutral hydrogen within, because of the intergalactic medium. And so this has been super hard to model in terms of Lyman alpha emitters, and so this is why it has been a really complicated problem so far. But let me already use this step which we have just taken to discuss with you what should happen to the evolution of Lyman alpha emitters as a function of time. So imagine that the universe is full of neutral hydrogen. If you have a low mass galaxy which produces Lyman alpha photons, as we have just discussed, these photons come out of the galaxy, they see neutral hydrogen, and they immediately get scattered out of the line of sight. However, if you have galaxies which either by themselves or because of neighboring galaxies can ionize large enough ionized regions so that by the time these Lyman alpha photons reach the edge, they are redshifted out of resonance with neutral hydrogen, then these Lyman alpha photons will actually reach the observer. So one of the key ideas in using Lyman alpha emitters to track reionization was that in the beginning stages of reionization, only those galaxies which were sitting in really clustered regions that could build large enough ionized regions around themselves would be visible as Lyman alpha emitters. So what happens as time goes by and the universe becomes more and more ionized? Perfect. So as the universe, imagine that the universe is now completely ionized, end stages of reionization. There is no neutral hydrogen left. So even these tiny sources would start becoming visible in terms of Lyman alpha emission, of course, imagining that you can detect every Lyman alpha photon that they are producing. So this was really the key idea, that in the initial stages of reionization, only clustered things would become visible as Lyman alpha emitters, with more and more star-forming galaxies, which you would just call normal field galaxies, would become visible in Lyman alpha as reionization progresses. So a couple of years ago, so now it's almost 10 years ago, Marco Castellano did this experiment in which he found 2 Lyman alpha emitters. And he said they are so close by, they seem clustered. And so he did really, really deep observations with the Hubble. And he found a huge number of tiny sources which were clustered around them. So this was one of the first indications that this was really a patch that was getting reionized at a redshift of 7 because this was living in an overdensity. So this was really one of the first observational detections of the fact that in the initial stages of reionization, clustered galaxies are preferentially visible as Lyman alpha emitters. Okay, now let's keep going and try to do this a bit more statistically. So far we have been looking at individual Lyman alpha emitters. But as we are discussing, Lyman alpha emitters are nothing but some sort of star-forming galaxies which are producing ionizing photons. So this experiment, which was done by a number of people, including Laura Penterici, is what fraction of galaxies have a visible Lyman alpha line as a function of redshift. The red points show you bright galaxies. The blue points show you faint galaxies. What I want you guys to look at is, let's just focus on the bright points. So you find that about 40% of star-forming galaxies are Lyman alpha emitters at a redshift of about 5.5 or so. They drop off both at high redshifts and at low redshifts. So now can you help me figure out what's happening? So why do you find fewer star-forming galaxies visible in Lyman alpha at high redshifts?
Less large cluster.
Perfect. So this is because of reionization. But reionization is, we just decided, or I hope I've managed to convince you, reionization more or less finishes by a redshift of 5, 5.5 or so. So why should fewer galaxies be visible in Lyman alpha as you come to low redshifts? What's killing off your Lyman alpha photons at low redshifts? Very good. Thank you. It is dust. So when you come to low redshifts, dust contents increase and they are able to really absorb your Lyman alpha photons with very high optical depths. And so this gives rise to this break. So this is not because of reionization. So if you want to look at Lyman alpha emitters as probes of reionization, it's better to look at this high redshift part. And you can use this to infer a neutral fraction of hydrogen as a function of redshift. And from Lyman alpha emitters, the constraints we are getting is that at a redshift of about 6, the neutral fraction is roughly 10-ish%. You can see error bars are really large. And this is because, if you remember, we said that the optical depth is proportional to 10 to the 5 times the fraction of neutral hydrogen. So if you have one part in 10 to the 5 hydrogen, which is neutral, you still get an optical depth of 1. So Lyman alpha is not a very sensitive probe of neutral hydrogen just because the optical depth is so high. Hence leading to these really large error bars. But in general, what we are finding is that the optical depth seems to be increasing as you go to higher redshift. So at a redshift of about 7-ish or so, it's anywhere between a few percent to 40% of the hydrogen is neutral. Let me now put all of this data that I have shown you together to show you the reionization history so far. So now this is the neutral hydrogen fraction as a function of redshift. And this is putting together all of these different probes that we have been talking about, including the CMB, including the Lyman alpha 4s, or including the spectra that we get from quasars. The dark gray region that you see is the region from CMB constraints. And all of these other probes are giving you all of these points that you see. Something that almost everybody is agreeing on is that the optical depth or the neutral hydrogen fraction is extremely low at redshifts below 5.5-ish or so. But the history of this process remains extremely poorly understood. So if you look at these different probes, if you ask when was the universe half ionized, you're going to get a redshift anywhere from a redshift of about 6-ish to a redshift of 7.5 or 8, depending on which probe you're selecting to look at the neutral hydrogen fraction. Yes?
Sorry, I'm a little confused because earlier you were saying that the Lyman alpha photon interaction with neutral hydrogen is a scattering process, but when we were computing like the Gunn-Peterson process, we were saying that it was absorbing, or?
No, it's scattering. So what's happening is whenever you have scattering, the Lyman alpha photon is traveling towards you, encounters neutral hydrogen, gets scattered out of your line of sight. So basically, this is a photon that is lost to you. So it's not absorbed. It's only absorbed by dust. With neutral hydrogen, it's really a scattering process. The problem is it's very rare that this would be scattered, or you would keep scattering Lyman alpha photons along the line of sight. Sorry, does that make sense? You know, so you have an equal probability of scattering them in any direction whatsoever. And so you're going to lose those Lyman alpha photons to your line of sight. Yeah. Sorry, does that make sense? Yeah. Perfect. Good. Okay, so I would just like to end by saying that I hope you guys can see from all of these different constraints that the end stages of reionization are kind of well constrained. We think it's ending somewhere between a redshift of 5, 5.5, depending on which probe you choose. But the high redshift history of reionization is really unclear. And this is work that is pre-James Webb, and I'm just going to show you how everything has just blown apart after the advent of the James Webb. So let me now move to the second part, which is we now know that the process of reionization happens. So the question is, okay, so what were the key sources which were driving the process? So can I ask you guys to, yes?
A couple of questions before.
Yes, sure.
So you've shown us that the ionization is inhomogeneous.
Yes.
Does that immediately mean that it's driven by brighter sources?
Oof, we're getting there.
Okay.
We're getting there in a minute. This is exactly the question I was going to ask you guys.
Oh, okay. Another question
Please,
is that
yeah.
we can go back to the CMB slide.
Yes.
The integral.
Yes.
So I'm confused. Right. So
Yes.
C sub R, is that the reionization redshift or the CMB redshift?
Sorry, ZR. Oh, yeah, no, this is the redshift of reionization, because what we are assuming is before the redshift of reionization, there are no free electrons, so no electron scattering. Instantaneous reionization, and then the whole universe is instantaneously full of electrons and protons.
Okay.
Yeah? Sorry, is that okay? Yeah? Okay, good. Yeah. You are not the only one who is confused. We have been struggling with this reionization history for decades. Okay, so yeah, I mean, many of you do know about reionization. So what do you think are the key sources which are driving the process? I don't need fractions. I just want to know what are the key sources you think, please.
I think up to recently the main sources were supposed to be stars.
Okay.
I think due to recent observation, we are currently re-evaluating the impact of AGN on the reionization, at least on the densest region.
Okay. This is a very good answer. Sure.
Mostly low mass star-forming galaxies, because even if there is a high aging fraction, it's a more amount of AGs that are being found at high redshifts. They also have to counterbalance the amount of low mass star-forming galaxies that have already existed at high redshifts.
These are very good answers. I was not looking for so many detailed answers, so thank you for answering the second part of this presentation. Okay, so these are very good answers. So what I'm hearing from you guys is two key sources: star-forming galaxies. We're discussing whether they're high mass, low mass, and AGN. Is there any other source we can think of? You know, I would still say that's, do you mean like heating from protoclusters, or do you mean star formation in protoclusters? So let's just say star formation and black hole accretion. Is there anything else? You know, I would still say that's star formation. You know, it's a product of star formation. So, I mean, you know, I was looking for more exotic scenarios. Very good, thank you. Dark matter decay was a strong contender at some point, but not anymore. It lasted it was a blip. But yes, this was something that people were considering. So if dark matter annihilates or decays, dark matter is literally everywhere, right? 30% of the total energy density is dark matter. So if you have contributions from dark matter, this would really be super important, but not anymore. So this is why it's an exotic source. So yes, so here we are basically going to try to focus on star-forming galaxies in AGN, and we're going to try and figure out what is the relative contribution as a function of time. Okay, so before jumping into the key sources, let's just do a very simple analysis of what are we actually trying to do. So if you guys remember, we were trying to calculate what volume fraction of the universe is full of ionized hydrogen. This is the basic reionization equation, which you will use if you're just trying to do reionization analytically. So as a function of redshift, how does the volume filling fraction of ionized hydrogen evolve? As you can imagine, this depends on a source term. So how many ionizing photons are you actually producing from your sources? Now, the sources can be whatever. We're going to discuss that in a minute. But this is not the whole story. So if you guys remember, we said you can produce a certain number of ionizing photons within these sources. But because of scattering or absorption by dust and neutral hydrogen, only a small fraction, which we're going to keep calling F escape, are going to come out of the galactic environment. So your source term is the number of ionizing photons times the escape fraction of these photons. And then we also have a recombination term, which is driven by the fact that if you have dense regions in the intergalactic medium, you can ionize them, but they are going to recombine on a certain time scale, which is basically driven by the local density. So if you look at the expression which is there, the recombination time scale basically depends on the average neutral hydrogen density at that redshift times what we call a clumping factor. So how overdense or clumped is the gas as a function of both space and time. And as I'm going to show you, this has been one of the key problems which we have been facing when we are trying to model reionization. So how many recombinations do you actually have in the intergalactic medium? So, okay. So now what I will do in the rest of this lecture is we're going to look at what were the key sources of ionizing photons in the early universe and what were their relative contributions. We're going to start discussing a little bit about how many ionizing photons could actually come out of the galactic environment. So what was this F escape, which we are putting in as a parameter? How did the clumping factor of the IgM actually evolve as a function of space and time? And something that is extremely relevant but is not overly discussed is, did reionization actually have any feedback on the galaxies that were driving this process? So let me start with the first part, which is looking at the key reionization sources. And you guys have really pointed out well that the two of the key sources we're looking at is any kind of star-forming galaxy, any kind of accreting black hole, could be low mass, high mass, so what you would call AGN or quasars. I think we can just call them high or low luminosity AGN. And then you have a lot of other possibilities which are considered much more exotic, so we're not going to look at them, but if you're interested, please come have a chat about this. So these include decaying or annihilating dark matter. Something we will touch upon very, very briefly is the contribution of metal-free stars, which are different, as you heard yesterday, to metal-rich star formation. And if you have exotic objects like maybe primordial black holes, so which are not astrophysical in origin, but which have a more, which find their origin, for example, in the in inflation. Okay, so let me start with what has changed since the launch of the James Webb. So till the James Webb, we had statistics on our galaxy population. Or let me actually, okay. So before the James Webb, from the Hubble, we knew galaxy populations out to a redshift of about 10 or so. This was the extent to which we could go. But with the James Webb, things have really exploded in this field, and we're getting luminosity functions out to redshifts of 15 to 20. So to remind you, a UV luminosity function is the ultraviolet luminosity at about 1500 angstrom in the rest frame of the galaxy. And what we're trying to do is look at how many galaxies you have per co-moving volume of space as a function of this absolute UV magnitude. So here, all of these different colored points that you see are observations from different groups. So here you can see luminosity functions going from a redshift of 10 out to a redshift of 15 to 20. These are upper limits, so I would urge you to disregard them. So just look at the data out to a redshift of 14. And I think for you guys, this is super normal to look at redshifts of like 20. But yeah, Rosa is here smiling because yeah, like when we started doing astronomy, the highest redshift galaxies we were discovering were at a redshift of, well, I was doing my PhD at a redshift of 6-ish. And so this was really the high redshift universe. And now suddenly with the James Webb, we're looking out well within the first few 100 million years of the universe. So what precisely, so let me just talk you through what actually changed when we started looking at this data. If in each panel you look at this blackish colored line, this is the ultraviolet luminosity function we expected pre-James Webb. So I think you guys all know galaxies form in a hierarchy. So you start with low mass objects at early times. They are going to merge together to form larger and larger structures. So this is your standard hierarchical structure formation scenario. Now with the Hubble, we were probing galaxy formation. So let me say this is a redshift of 10. Till a redshift of, between a redshift of 0 and 10, things kind of seem to make sense. So, you know, like you would naturally expect, well, okay, structure formation isn't doing anything crazy. So if you would look to even higher redshifts, you should basically be able to match your observations. Because what should change at high redshifts? Now, a key problem is at a redshift of 10, your expectation, the observations from the James Webb kind of seem to match what we expected from the pre-James Webb era. But the moment you go to redshifts above 11, compare the points that you are measuring here. I completely know you guys cannot see all of these points. There's too many and there's maybe too faint. But yes, I'm going to put the slides online so you guys can then have a proper look. This blackish line is what we were expecting would be the evolution of the UV luminosity function. But at all redshifts above 11, you're beginning to see an overabundance of bright things, which almost nobody was predicting. So this is completely unexpected. And so now, can I ask you guys to, I mean, the solutions are on the board, but I will remove it. And I will ask you, okay, so how do you boost up the luminosity of galaxies? What can you do? Can we have a chat about some of the different things?
I just have a very nice question.
Yes.
How to be sure, the low amount of points we have, how to be sure it's not just some selection effect? Because at this very high redshift,
Yeah.
you can only detect very bright objects, which could be very rare.
Okay, no, it's a good point, yeah.
As the opposite of this assembly, I am not used to such high redshift.
Yes.
So I am wondering.
You're not the only one. I mean, nobody was prepared for this. You know, we were always making predictions out of redshift 15, but we were not prepared for this. So, okay, so it's a really good point. So, I think one of the things which the James Webb is doing is it's looking at tiny blank fields. So you look roughly at 10 by 10 co-moving megaparsec, which is a tiny patch of the sky. But then we're also doing surveys where we're looking behind clusters. So these are called lensed fields. And for every lensed field, you also have a blank field. And the idea is to really get an idea of cosmic variance. So how much can your number densities change from one field to the other? So now in this data that I'm showing you, we have more than 40 fields. So these are 40 individual pointings. And so it's no longer, it is still limited by cosmic variance, but not as much as you would expect. And it's not only bright things that we are detecting with the James Webb. So with lensing, for example, we can go down to really low luminosity things. So here, for example, we are probing things which are which are minus 17 in terms of the UV magnitude. So these are things which roughly have a star formation rate of 1 solar mass per year. These are really, really tiny, extremely faint things, and we're able to see them purely because of lensing. So at the low mass end, you are correct. At the low luminosity end, we don't have a specific problem, but yes, it's arising more at the bright end. And people have spent a lot of effort to confirm these sources because we were just looking at them photometrically. And for many of them, we were not completely sure of the redshift. But as we have done spectroscopy for more and more of them, the success rate is approaching 80%. So most of these sources are at the redshift that we claim. So, okay, so if these sources are indeed true, what could actually give you an over-density of bright objects? So let me show you this on the board just to clarify things a little bit. So what we are trying to do is look at the number of objects per co-moving volume as a function of the UV magnitude. Here is your data. This is what theory is predicting. So there's just too many bright things. So how do you make things brighter? Very good, okay. So are you saying it's things which are really exploding? So they are, in principle, they should be here, but because they are exploding, they seem brighter than they should be. Okay. Yes, so some kind of an Eddington bias that it's easier to see low mass stuff scattered into high mass bins or high luminosity bins. It is. Okay, yeah.
Increased star formation efficiency.
Okay, very good, yes. I love how you guys are coming up with very nice solutions, yes.
Also, we can maybe form more massive stars related to the initial mass function,
Very good.
of the initial
Okay.
mass function.
Very good. And why should the initial mass function change with redshift?
I think it's a big question of modern cosmology.
I mean, sure, like, I agree completely.
I see a lot of debates around the high redshift initial mass function.
Okay, so in principle, what should change your IMF? And this you should all remember from Andrea's presentation. What is one really crucial thing that can change the initial mass function? Very good, metallicity. So as you go to lower metallicities, we can, in principle, transition, if this is the number of stars as a mass m, you can go from your typical saltpeter or whatever to a much shallower slope. And this can be driven by low metallicity, high pressure. And so as you go to higher and higher redshifts, in principle, you expect galaxies to be more and more metal poor. And so perhaps this is something that is driving an evolution in the initial mass function. Okay, what else? Sorry? Who said dust? Very good. This is Andrea's favorite solution. So the best solution is the evolving IMF. Okay, so thank you guys for kind of coming up with all of these different solutions. So yeah, so the two that I'm going to focus on are that the initial mass function becomes more and more top heavy, so it becomes more and more flat as the metallicity decreases. And so this is a mass and redshift dependent effect. You can also say, well, what if things, for whatever reason, are just more efficient in forming stars as you go to higher redshifts? So all of the other possibilities that you've raised are here. So there has been a huge amount of effort dedicated to trying to understand these early sources because, well, I mean, this is really fundamental to understanding the first billion years. And so here is one solution which Andrea proposed, which was that as you go to higher and higher redshifts, things are just becoming unattenuated. So dust is no longer able to attenuate the light, which it could have. And so most of the UV light that these systems are producing is basically able to reach the observer. So dust attenuation becomes less and less important as you go to higher redshifts. You also raise the issue of bursty star formation. So here the idea is I have a galaxy which is forming stars at, you know, let's say 1 solar mass per year. It's sitting here in the luminosity function. But if it has a burst, the luminosity can brighten temporarily. And so it can make it more luminous compared to what you actually expect. Not all of these can be bursty for a lot of different reasons. But yes, some of them could be bursty. Something that we didn't touch upon is the fact that what if in these galaxies they are powered not just by star formation but also by black hole accretion? Then there are two sources which are going to add to the total luminosity. And so here you could have your galaxies which have star formation plus a small contribution from black holes, making them brighter. You could also have something which is called feedback-free star formation, which I'm not going to talk about because it's a kind of exotic scenario for producing these early galaxies. But just to give you an idea that as of now, we have a number of, so there's at least 6 different pathways to explain this overabundance of bright objects in the first billion years of the universe. Now, as you can imagine, this also has consequences for reionization, and I'm just going to show you in a minute how. So if you remember, the reionization source term that we wrote was how many ionizing photons you produce. And this is, if it is from star formation, it's basically proportional to the star formation rate. So the density of, so let me call this rho, is basically going to be proportional to the density of star formation in the universe. So let me assume all ionizing photons purely come from star formation. So what I can do is I can look at the evolution of the star formation rate density as a function of redshift to get an idea of how many ionizing photons per co-moving volume are my sources actually producing. So let me show you the change, which is now much more dramatic. So the blue points that you see here are the star formation rate densities that we had inferred from the Hubble Space Telescope. You can see that there was a continuous decline in the star formation efficiency with increasing redshift. This is exactly what you expect from standard structure formation scenario. As you go to higher and higher redshifts, you have fewer halos. Star formation efficiencies are, even if you keep them constant, the total star formation rate density will go down as a function of time, just because you have fewer bound structures. Now, the orange points are the star formation rate density estimates that we have from the James Webb. So immediately, you can see there is a problem with the HST. We thought that the star formation rate density was decaying by more than 2.5 orders of magnitude. between a redshift of 6 and a redshift of 10.5, 11-ish. So by a redshift of 11, the star formation rate density was supposed to become really negligible in a certain way. But now, the data from the James Webb seems to indicate a different slope. So if I want to fit all of this data, you can see that there is really a very long tail which is extending out to high redshifts. So statistically, this is telling you that there is a lot of star formation per co-moving volume out to redshifts of, this is out to a redshift of 13, but this is a very old review, which is almost like 6 months old, so everything has changed. So now we have confirmed sources even out to redshifts of 14, which you can see through their Lyman alpha emission line. And so this is becoming a huge problem because this basically means you have a huge number of ionizing photons. So the ionizing photon density is much higher than what you were expecting. So in general reionization models, we were really underestimating how many total ionizing photons we would actually have for the process of reionization. Now, I want to take one step back and just show you one caveat. So generally, what you will find people doing is they will say that the ionizing photon production density is proportional to the star formation rate density. So this is a generic assumption many people will make. If you have more photons, if you have more star formation rate density, you have more ionizing photon production density. Now, let me just show you what a key issue is. So let me just define one more quantity before we go on. So something that Laura is going to teach you is what is called psi ion, which is the production rate of ionizing photons per unit of UV luminosity, because this is actually an observable. You can look at how many ionizing photons you produce, you can look at the UV, and you can do a ratio, and this is the term that most observers will put into their reionization equations. So now let me show you what is happening to this ionizing efficiency, so production rate of ionizing photons as a function of UV luminosity. This actually is very sensitively dependent on the age of the stellar population. So I know you cannot read numbers, but if you just follow this purplish line, this is for, actually just look at any of these lines. So this is for a star formation rate of 1 solar mass per year. When you have new stars forming at about 1 million years, the ionizing production efficiency is very high. And this then drops with time because the production rate of ionizing photons drops off faster than the production rate of UV photons. So this is independent of whichever model you use. The ionizing efficiency will drop off with time. But we're not talking about huge periods of time. Here, you are going from 1 million years to 10 million years. So within a period of about 10-ish million years, your ionizing efficiency will start to drop by a factor 3 to 5, depending on which stellar model, population model you're using. By the time you go to a few tens of million years, this will decay by about an order-ish of magnitude. So how many ionizing photons you're producing really sensitively depends on the age of your stellar population. A second complication is the dependence on metallicity. So here, the purplish line that you see is for 10% solar metallicity, and this yellowish line that you see is for solar metallicity. So now remember, these are both POP2 stars or POP1 stars, so it's both metal and rich star. This is not comparing metal-free, metal-rich stars. But if you go from a metallicity of 10% solar to 100% solar, the production efficiency scales by a factor of 5 to 10. So as you increase the metallicity, you are producing fewer ionizing photons per unit UV. So we made this assumption, right? We said from the star formation rate density, you can directly infer the density of how many ionizing photons you have. But we're completely ignoring any dependence on the stellar population, including...
We have about 5 minutes to coffee, so when you can
what?
break,
No, I thought I had to then, okay, I have to speed up a lot, so drink a lot of coffee and come prepared. Okay, let me just finish this and then I can break. Okay, this is a disaster. Okay, good, anyway. Okay, so then let me show you the second thing. So we just discussed an evolving IMF can be a solution for these extremely bright things we're seeing. If you increase, so here again, production efficiency of ionizing photons as a function of UV magnitude. If you have things that have really top-heavy IMFs, you can produce up to 3 to 5 times more ionizing photons per unit of UV. So this is the second problem that we have, that even if you have the star formation rate density, and let me call it the density of star formation rate, if you try to convert this to a density of ionizing photons, this actually depends on the age of the stellar population, the IMF, metallicity, and these are just some of the most fundamental parameters that your ionizing photon production rate will depend on. So please keep this in mind, that when you use these translations, this is really 0th order, but the actual numbers can differ really depending on what you think your underlying stellar population is. So, I mean, just tell me when you want me to stop.
You can go on, it's fine for like 10 minutes more, because you started a bit late, so don't feel pressured.
This is so kind. Okay, very good. Okay, so let me show you this new result that came out when we had James Webb data as early as 2024. So now we are in this situation where you have really a lot of star formation rate density. It's not decaying. So if you guys remember, we said the star formation rate density keeps extending out to high redshifts. This is what we were expecting to happen. So you have this huge amount of photons which are extending out to redshifts of 14 or even 15. So now if you have these many ionizing photons, imagine all of them are able to escape out of the galaxy. So here I'm going to assume an F escape, which is 1. So every ionizing photon you produce can basically come out of the galaxy. Let me show you what happens to the electron scattering optical depth as a function of redshift. So this is the value that we measure from Planck. That is the horizontal dot dashed line together with the error bars. If you assume the model in which the IMF evolves as a function of metallicity, the optical depth that you find goes up to about 0.09. So you are predicting a much, much higher electron scattering optical depth. And this is because reionization starts early, as a result of which the total optical depth increases. Even if you assume the model in which we said, what if the star formation rate efficiency increases, you get basically the same result. So it doesn't really matter what you do. If you want to be compatible with the star formation rate density that you see from the James Webb, you are predicting an electron scattering optical depth that is very high compared to what we are measuring from CMB data. But this is one of our most fundamental constraints for people started writing papers saying, are we in the time of an overproduction crisis? Suddenly, we seem to have too many ionizing photons in the universe, and especially really early on. You can also try and see what happens to the history of reionization. So this is the volume filling fraction of ionized hydrogen. So what fraction of the universe is filled with ionized hydrogen as a function of redshift. This is the data that we had. So this is the same data that we were discussing in the first part, which is the data from the CMB, Lyman alpha, quasars, et cetera, indicating that reionization finishes at a redshift of somewhere between 5 or 6. Again, the same problem. If you have too many ionizing photons, you will reionize the universe too early on. So here, depending on if you use the evolving IMF model or the evolving star formation efficiency model, you find that you are reionizing the universe somewhere between a redshift of 8 to a redshift of about 11.5. So there's too many ionizing photons that we have if we take James Webb data at face value. Okay, so now I think we should actually break here, because when we come back, I would like to ask you guys for solutions to this overproduction crisis problem, which we have resolved to some extent. But yes, please go have a think. And if you want to chat during coffee break, just come chat with me. Yeah, good. Thank you.
So I propose we break for 25 minutes.